Alright, cardiovascular system lecture. Let's just get into this. We'll see how quickly we can get it done. Haha. I don't do anything fast. Alright, so the functions of the cardiovascular system are transport. You all knew that. Oxygen, right? But also nutrients, waste, hormones, lots of things. Right? We transport all of it. And there's also some very important immune functions in the cardiovascular system that we'll go into more detail about in the next lecture. But suffice it to say, the cardiovascular system is the main transport system for white blood cells. And then lastly, your cardiovascular system does a great job regulating temperature. Warm blood in the core can be sent out to heat the extremities. So, great. Blood vessels are the part and parcel of the cardiovascular system, right? Everything travels in a closed system of vessels. They include arteries, veins, and capillaries, right? And then we'll special mention the lymph vessels because that's very important. And very few non-majors have a pretty good working knowledge of the lymphatic system and what it is. So first off is arteries. Arteries are the thickest vessels in the body, right? These are extremely thick, in large part due to the thick, smooth muscle wall that lines the arteries. Arteries carry blood away from the heart. In fact, that's all you need to be considered an artery, is to carry blood away from the heart. So, for the most part, when people think of arteries, they're thinking of oxygenated blood, but that is not always true, because the only requirement is to carry blood away from the heart. So if you have blood coming into the heart from the body, right? There's a sort of closed system here. We have blood going away from the heart to the body. And then there's a very important thing going on here in that we also have blood that goes to the lungs. Right? And this blood going from the heart to the lungs, well, that's going away from the heart. Right, so this here, this is the pulmonary artery, and it carries deoxygenated blood that has come from the body to the heart. Then from the heart, that deoxygenated blood will go to the lungs and become oxygenated. So, the pulmonary artery is the only artery that is not carrying oxygenated blood. As I said, artery walls are very thick, and they have very thick muscular lining. That muscle allows the arteries to both expand and relax. Expansion of arteries is, we use the word dilate when we say expand. And so the arteries can expand and relax that muscular wall, and that increases flow rates, increases the amount of blood traveling through there. Really, what that is about is resisting blood pressure. Right? When the heart here pumps, it is a powerful muscular action. That first pump, which sends blood into the main artery that has to go send the blood to the rest of the body, right, there is a lot of pressure there. And the artery connected to the heart has to be able to expand and relax that wall in order to not get damaged by the large pressure it receives when the heart pumps. So that muscular wall is great for being able to alter, right, the diameter of the blood vessel wall, right? All this vessel musculature also allows vasoconstriction, which is when we contract and reduce the diameter, right? So we can constrict blood flow to different areas as well. So the arteries have these nice thick muscular walls because they are handling the highest pressure in the body, right? They must withstand high pressure. So those thick walls and that thick muscular layer allows them to react and compensate for the pressure from the heart, from the blood flow coming off that heart. It is the arteries where you can feel the pulse. So here's a little chart of common arteries, right? These are going from the heart to the body. So in your neck, we have the common carotid arteries. These are often named generally for where they are. Also coming off your heart are these two little arteries that arc a little bit like this. They're sort of right around my clavicle. Oh, just slightly beneath. They're subclavian, below the clavicle arteries. Then we get into the armpit, and in your armpit here we have the axillary arteries. If you know much about Latin, brachial is a word for arm. So the artery running through your upper arm is the brachial artery. We separate out into two arteries on the forearm that happen to go along the two forearm bones, the radial artery and the ulnar artery. So you have your radial artery, or your radial artery here, and your ulnar artery here. All right? So far, easy. Named for kind of where they are. Then you have your aortic arch, right? And that aortic arch is the artery coming off the heart. And it's going to curve downward to supply everything beneath your, arms and head. And we have the thoracic aorta, the part of the aorta that travels through your chest cavity. Coming off of there, we have important arteries, like the arteries that feed your kidneys, the renal arteries. They feed your kidneys. Right? As we get down to this area here, we have some arteries that pass through a portion of the hip. This portion of the pelvis is called the ilium. So they call it the iliac artery. Right? So we have this separation into left and right. And then from there we just go down into the legs. And the artery traveling along your upper leg is the femoral artery. Right? Fancy, just like axillary is the fancy term when we're describing the armpit area. Popliteal is the fancy term when we're describing the kneecap area. Oh. Whoa, hey. Stop it. The kneecap area. That's popliteal. Then we have an artery in front and an artery behind the tibia, the big bone in your lower leg. So these are just selected arteries for you non-majors to know. Just for funsies, these are different places where you can feel the pulse in your from your heart. You can feel your pulse in these different spots. Good times. There we go. Now let's talk about veins. Veins are pretty cool. Veins carry blood back to the heart. If you're going towards the heart, you are a vein. So, in general, most of the veins are carrying blood from the body to the heart, right? So, arteries carry oxygenated blood from the heart to the body, and then the body gets that oxygen, and then deoxygenated blood is carried back from the body to the heart, all right? You have sort of two circuits. All right, so here's our body circuit. Right, in which we have arteries carrying oxygenated blood. And veins, right, at the body we have O2 exchange. So here, now that the body has grabbed that oxygen, whoa, this thing is getting away from me apparently. Now that the body has grabbed that oxygen, right, whoa, this software is freaky. This drawing is terrible. Where's my eraser? No. No. That's so much better. Okay, now here we're going from the body to the heart. So this is a vein, and it's carrying deoxygenated blood. Now there's an entirely separate circuit, though, and that goes from the heart to the lungs. And from the lungs back to the heart. Right? So heart to body. Body to heart. Right? And then from heart to lungs. This is going away. So this is the pulmonary artery, and it is deoxygenated. Whereas here we have going towards the heart, this is the pulmonary vein. And it is oxygenated. So basically, if you're on the body circuit, arteries carry oxygenated blood away from the heart, veins carry deoxygenated blood back to the heart. If you're on the pulmonary circuit, the lung circuit, arteries carry deoxygenated blood away from the heart to the lungs, and veins carry oxygenated blood from the lungs to the heart. Now, an amazing thing about veins is they have very thin walls. They do not nearly have as much muscle. Much less muscle. Much less muscle in the veins. This is because there is very little pressure in veins, right? When you get to this part here, the body, in reality, what's happening is that our blood is being pushed through this little circuit of ever smaller and smaller and smaller vessels. These are going to be the capillaries we'll talk about. But they're so small that blood slows down so much that by the time we get to the veins, we are at extremely low pressure. Right? Veins do not have to deal with pressure. They do tend to have a large open diameter to them. They're pretty cool because they have valves, venous valves. These are important because veins have so little pressure in them that blood in a vein that happens to be going vertically, like maybe it's the blood in your legs, right? If the blood is in the vein and you stand up against gravity, gravity will cause the blood to backflow. Right? The pressure is so low that blood can backflow in veins. So veins have a series of valves that can squeeze shut. And thus, if blood is falling back down, it can't backflow beyond that valve. And there's only one way for blood to go. Right? So that's them venous valves. Prevents backflow of blood because there's so little pressure that there's not enough pressure in the veins to keep the blood going one direction. And what's fascinating about this is that it's not really the heart that's pumping blood through your veins. In fact, it's your muscles. So here's some basic veins. So we separate veins into basically veins coming from above and veins coming from below, right? So we'll start with the extremities because, that's where the blood is coming from. There's a lot of complicated names for a lot of this stuff, so I've stuck to the simple ones. So here we have the brachial vein in your upper arm, and it merges with the armpit vein, the axillary vein right there. And then over here, right, we have a little merging with blood coming from the head and blood coming from the arms. Well, brachio arms, cephalo head, the brachiocephalic vein. Right? That's carrying blood from both the head and the veins. Here's the subclavian, just like with the arteries. There's a vein right underneath your clavicle. And then coming from your head in your neck there are the external jugular veins. Okay, so from the arm we go brachial, axillary, subclavian. From the head we go external jugular. They meet up, creating something called the brachiocephalic vein. And then the left and right brachiocephalic veins meet up and create the superior vena cava. Superior because it's coming to the heart from the upper body. So it's coming in from above. Okay, extremities. We'll start low with the feet. We have the posterior behind the tibia vein. So it's behind the tibial bone. And then we've also got a vein in front of the tibia. So posterior and tibial veins. Passing, by the kneecap area, popliteal vein. Then we have the femoral vein, right? And then we have this two basic branches on the left and right, that travel along the part of the pelvis called the ilium, the common iliac vein. And when the common iliac veins meet up, they create this large vein, bringing blood in from the lower part of the body. So it's the inferior beneath vena cava. Then, of course, always important to mention the vein that comes from the kidneys and the hepatic vein coming from the liver. Right? So these are just some nice veins because they are named for where they are. Now let's talk about those venous valves. The valves are really cool because they are extremely important to how blood moves through the veins. And the way blood moves through the veins is via skeletal muscle. Right? So veins tend to be close to the bones. And they tend to run in the muscle. And what happens is that when a muscle contracts, right, it squeezes a vein. When a muscle contracts, it squeezes that vein. Right? So you have a contraction point putting pressure up against a vein. Right? So beneath that contraction area, my valve is shut, and then the force of contraction, right, squeezes this valve open. So as the muscle contracts, the blood is pushed forward. And when the muscle relaxes and takes pressure off, right, the valve below it is still shut, but when it relaxes, it's not squeezing blood anymore, and this valve snaps shut. So as our pressure releases, the valve above the muscle snaps shut. Right? So it's actually muscle contraction that's pushing blood through the veins. And then muscle relaxation, it's just contraction and relaxation of the muscles that's causing blood to move through. It's really cool. A lot of your muscles can be thought of as little secondary hearts. One of the muscles most important to pumping blood from your legs to your heart is the gastrocnemius. If you've already forgotten, that's the calf muscle. Some people call the calf a secondary heart. The contraction relaxation of the calf muscle is vital to getting blood back to your heart. Such that if there are people that stand at attention with their calves too constricted, like if they don't know how to properly stand at attention and they just keep their legs just constricted, it'll keep blood from flowing, and they'll actually get not enough blood going back to their heart to get enough pumped around to supply the brain, and people have been known to pass out. So if you are standing and you've got your leg muscles contracted, you can pass out because they are not doing their job of contracting and relaxing to push blood towards the heart. It's just so cool. Okay, capillaries, the interface. Right? So capillaries are pretty sweet for a number of reasons. If I were to draw a capillary, I might draw it up like this. So this is the capillary wall. And in many cases, it is 1 cell thick. And then the other main thing to think about is that capillaries are so thin that they're often thinner than the red blood cell, smaller in diameter than a red blood cell, which means a red blood cell will actually end up getting sort of squeezed as it travels through there. And basically, we're going to have, out of the capillary thin walls, oxygen and nutrients and blood plasma. Those all come through out of the capillary walls. Oxygen, nutrients, blood plasma, hormones, everything else, right? These are coming out. And then diffusing in would be things like wastes, signals, like hormones. We'll put hormones on both the coming out and the going in. So, things cross the capillary wall. These are the smallest vessels in the body and the most numerous vessels in the body. You have capillary networks basically everywhere. Anywhere your body can be pink, there's dense capillary beds underneath there. I guess pink is a real white guy thing of me to say. Anywhere that you have blood flow under the skin, there's massive capillary beds. Arteries are the interface between where blood from arteries... capillaries are the interface from between arteries and veins. If you're on the body circuit, arteries carrying oxygenated blood bring that blood to the capillaries, and the oxygen and nutrients and what have you exit the blood, and it becomes deoxygenated, collecting back into the veins and going back to the heart. Thinnest walls, often 1 cell thick, and this is where substances diffuse out. Right? So, anything, whether it's O2 or nutrients or hormones or anything, they are diffusing out in plasma. The liquid actually leaves, the liquid portion of your blood actually leaves your blood flow at the capillaries. Because, you know, you might have a capillary right here, and then you have multiple layers of cells that need to get, you know, nutrients and oxygen and everything from this, right? And so it's plasma diffusing out of the blood that then can continue diffusing through the layers of cells. So we have to have blood plasma exit the blood. So, oxygen, waste, nutrients like glucose diffuse out and in. Okay. So, here's where I mentioned the pulmonary circuit, right? So, heart to the pulmonary artery to the lungs, lungs to the pulmonary veins to the heart. This is not difficult, right? Pulmonary circuit goes like this. Lungs. Right? Here's our pulmonary veins. And here's our pulmonary arteries. Not hard. Body circuit. Again, not hard. All right, here's our heart. And the first vessel coming off is the aorta. That's the first artery coming off. And we go from the aorta to the body, basically. And then from the body to the heart. Now, it's worth noting that, as I said, blood comes from above and below. So when we're coming back into the heart, the blood coming from the head and arms is coming through the superior vena cava. And the blood coming from the torso and legs is coming through the inferior vena cava. Alright. Inferior and superior vena cava to the heart, and so on. Now, there is a distinct order to this. So, we'll start with the heart. And the direction of blood flow is we go from the heart to the pulmonary arteries. The pulmonary arteries to the lungs, where oxygenation occurs. That oxygenated blood is carried from the lungs by the pulmonary veins back to the heart. From there, the heart pumps that oxygenated blood to the aorta, which then goes to the body, the head and arms and the torso and legs. And then from the body, the head and arms go into the superior vena cava, and the torso and legs go from the inferior vena cava back to the heart, and you're ready to go all through the whole thing again. This is the basic flow. So when we talk more about the heart, we'll talk more about that. But here you go. This is a little map including selected little organs and stuff, right? So, boom. So here's the pulmonary circuit. And then here's the body circuits. And they've gone ahead and separated it out into head and arms and torso and legs, which is nice. They've also got a nice heart here. So you can see the first stop in the heart is right here. And then we go into this part of the heart, and then we go to the pulmonary circuit, and then we come back into this part of the heart here, and then we go from there into the body circuit. This nice little flow map with some organs and whatnot. All right, now it's time to talk about the lymphatic vessels and what they do. Lymphatic vessels are very important because of what I said earlier in the capillary section. And that's that at your capillaries, right, there's my one cell thick capillary, nutrients, oxygen, and what have you diffuse out in plasma. But you notice that each time your heart beats, your body does not swell up with fluid like a big bag. And that is because the blood plasma that exits here gets carried back to the body. Right? It is carried back to the blood system. Right? So, I said body, back to the blood vessels. Well, basically, out in the tissue, you have these little openings. All through the tissue, basically anywhere where there's capillary beds, there's a bunch of little openings here. That each opening is basically a bunch of little holes, pores, and we have one-way pores. Blood plasma travels through those pores into lymphatic vessels, lymph vessels. Anywhere you have veins, you have lymph vessels. The lymph vessels follow along with the veins. So lymph vessels are the openings to lymph vessels are all throughout the capillary beds. Fluid from the capillaries goes into your tissues, and it gets back to the blood by entering the one-way lymph vessels. So they pick up blood plasma, and then traveling alongside your veins, so the muscle is pushing the fluid through, it moves through the body, right? Occasionally there are spots like in your armpits or somewhere around here and here you have little nodes, right? So a little sort of widening of a lymph vessel. This is a lymph node. And there's details to talk about later, but basically inside a lymph node you have a bunch of little immune cells. So these have a tendency to inflame when you're infected with something. So they can swell up, which is why your doctor feels along here. If the infection can get into your lymph nodes, it causes them to swell. So it's kind of cool. So the blood plasma that's in there is acellular. It's not carrying things like tissue cells and blood cells. So there's some immune cells in there, but generally it's not carrying cells, so we just call it a lymphatic fluid. There's no red blood cells in it, so it's not red in color. Lymphatic fluid is clear. In fact, if there's no, let's see, how do I want to put it? One of the first things that happens after you get a small cut is the muscles around that cut, the muscles around the arteries feeding that cut area vasoconstrict and get thin and cut off blood flow, right? So if you put pressure on there and you can get those blood vessels, those little arteries, to constrict and cut off blood flow, the bleeding will stop. But oftentimes you'll still get clear fluid coming out of there, and that's because lymph vessels don't have a muscular lining. And so as long as a lymph vessel is cut, it'll sort of bleed its clear lymphatic fluid into that cut area. So you often see lymphatic fluid in your cuts. No blood cells in lymphatic fluid. Then you have those lymph nodes, which are full of immune cells, which allow filtering of whatever's going through. So you can filter out pathogens and things like that. Anyway, this picture isn't ideal, but all these little green things are lymphatic vessels going one way. One way. And they all integrate from the left side, the right side, from the head, from the torso. They all sort of integrate and drain into the large veins near the superior vena cava, right? Usually it's the subclavians. I think it's the subclavians. I'm doing that from memory, though. Anyway, they drain into the large veins. Not the vena cavas themselves, but the large veins above the superior vena cava. Okay, time to talk about the heart itself. Our Latin prefix for heart is cardia, right? So, the location of the heart is the left side of your body, just left of center, nestled in your left lung. Your left lung is actually smaller than your right lung because it has to make room for your heart. So, it's in the left side of your chest cavity, nestled up against your lungs. The wall of the heart is called the myocardium. Myo, if you'll remember, is our prefix for muscle. So the heart is basically a gigantic muscle, right? So when you look at a heart and its chambers, the majority of the walls of a heart are muscle. Right, so here's our little chambers, which we'll talk about, and all the wall is muscle. It's chock full of muscly goodness. So, muscle cardium, heart, is the heart wall. All sorts of cardiac muscle up in there, and lucky for you, it's completely involuntary. Alright, the anatomy of a heart. Now, it's important to mention anatomical position when talking about the heart, because on things like pictures and exams, it might look wrong to you when they label the parts of the heart into left and right. Because if you look at this image, you'll say, wait a second, left makes the L? Why is this the right atrium? And that's because in all things anatomical, all images are of a person facing you. So this heart belongs to the person standing in front of me. So when you look at this image, right, you are looking straight on. So the left side is here, the right side is here, and when you turn it into a picture, there, we now have the little switch. Because of anatomical position, when you look at any diagram, right, the right is going to be the left side of the image, and the left is going to be the right side of the image, because it belongs to the dude or person who is standing in front of you, like this. These fingers got all messed up. Whatever. Sanctuary, sanctuary. Anyway, here's this person's heart. Right? So, this person, this is their left side, and this is the right side of that person. So, hence. Okay, there are 4 chambers to a heart. The chambers are separated into 2 kinds, atrium and ventricle, and they are named for which side of the body they are on. We have the left and the right atrium, which are sometimes, these are the chambers blood first enters into, and then we have the left and the right ventricles, which are the second chamber blood goes into. So, if you look at a heart, I like to draw because it means you might be drawing with me, hopefully. Alright, so here's my atrium. Atrium, ventricle. So this is my left atrium and my left ventricle, and here's my right atrium and my right ventricle. Between the chambers, we have valves, and between the ventricle and vessels, we have valves. Right? So these valves have pretty simple names. The valve here that is between an atrium and a ventricle is, amazingly enough, called the atrioventricular valve. Affectionately known as the AV. So, between the right atrium and right ventricle, you have the right AV, and between the left atrium and the left ventricle, you have the left AV. Then we have a second set of valves coming out of the ventricles, and these are named for where blood is going and kind of what they look like when they're shut, right? So I tried to really sort of emphasize this kind of semicircle thing going on, because these are semi-lunar valves. Semi-lunar. So from the right ventricle, we go to the lungs. So that's the pulmonary semilunar valve. And then from the left ventricle, we go out to the aorta, and we have the aortic semilunar valve. All right? So, pulmonary semilunar coming from the right ventricle, and aortic semilunar coming from the left ventricle. Whee! Okay. So, nice little picture of the chambers, and oxygenation. So we have deoxygenated blood coming from the body, entering from the inferior vena cava, from the torso and legs, and the superior vena cava from the head and arms. Right? And then we enter our atrium. Right? This is our right atrium. And we pass the right AV, and we enter the right ventricle, and we pass the pulmonary semilunar. Well, that is getting tough to read. And we go out to the right and left lung. Right? And then we come from the lungs directly into, so from the pulmonary vein here, directly into the left atrium. From the left atrium, we cross the left atrioventricular valve, and we enter the left ventricle. From the left ventricle, we pass the aortic semilunar valve, and we enter the aorta. Whee! And here it is in text. The right atrium, blood in the right atrium passes the right atrioventricular valve into the right ventricle. From the right ventricle, blood passes the pulmonary semilunar valve into the pulmonary arteries. From the pulmonary arteries, we go to the lungs where oxygenation occurs, and oxygenated blood enters the pulmonary veins. From the pulmonary veins, we drain into the left atrium. We pass the left atrioventricular valve into the left ventricle. From there, the left ventricle pushes blood past the aortic semilunar valve into the aorta and the body. Whee! So, nice big image here for labeling. Here's the superior vena cava. And here's the inferior vena cava. You'll notice there is no valve between the blood vessels and the atriums, right? There's no valves. This is because the pressure is so low that you don't want to add something to constrict blood flow. Remember, vein blood pressure is extremely low. So if it's able to be pushed in, by all means, let it push in, right? What restricts blood flow throughout the heart is the closing and opening of the heart valves, right? So here is my right atrium. I'm killing you with all this writing, but you might just have to do it. Here's the right AV, atrioventricular valve. Then we enter into the right ventricle. Now, this is all heart muscle, right? And I kind of wanted to point something out. The ventricle walls are not of the same thickness on either side of the ventricles, right? Here on the right ventricle, you can see it's a much thinner wall than the left ventricle. Left ventricle has a much thicker wall. And it's actually really simple as to why that is, and that's that your heart is here and your lungs are right next to it. You do not need much force to send the blood from the right ventricle out to the lungs. This is just not necessary. So the muscle by the right ventricle that pumps blood, right, is thinner, right? It's ventricular wall. It's the ventricular walls that pump blood. That is what does the pumping of the blood, the ventricular walls. All right, so we've got blood draining into the body from the superior and inferior vena cava into the right atrium. It passes the right atrioventricular valve and it enters the right ventricle. Then the ventricle pumps. When the ventricle pumps, this valve here, the right atrioventricular valve, snaps shut, and my pulmonary semilunar opens. Then blood enters the pulmonary arteries. And we go to the right or the left lung. Then from the right or the left lung, we enter the heart from the pulmonary veins. Both of these are pulmonary veins. One coming from the left, one coming from the right, meeting up here. Right, and we enter into the left atrium, wherein we pass the left atrioventricular valve and we enter the left ventricle with that extremely powerful muscle wall, because when that muscle wall pumps, the left atrioventricular valve snaps shut, and we push open the aortic semilunar valve. And our blood passes into the aorta. Alright, we're just doing this over and over and over again for you people, so you get the idea. Alright, and then this is just like a synthesis of all the information. So, everything's labeled. And then here we actually synthesize it together with the body and pulmonary circuits. Right? So, here we go. Inferior vena cava, superior vena cava into the right atrium. Past the right atrioventricular valve into the right ventricle. Past the pulmonary semilunar valve into the pulmonary arteries. To the lungs. To the right lung and the right pulmonary vein, and the left lung and the left pulmonary vein. Back to the left atrium. From the left atrium through the left atrioventricular valve into the left ventricle. Then from the left ventricle we get that big pump past the aortic semilunar into the aorta, out to the body. And from the lower body we drain into the inferior vena cava. From the upper body we drain into the superior vena cava. Woo! Woo! Put it all together. And then this just has arrows. And everyone loves animated pictures. Whee! So, it's nice because, again, we've got the parts right here. Here's the lungs, right, for our pulmonary flow. So, right here we have the inferior vena. Wow, that color is no longer helpful. Let's go for this ridiculously bright blue. Right here we have our inferior vena cava. Up here we have our superior vena cava. Here is our right atrium. Here's our right AV. Here's our right ventricle. Here's the pulmonary semilunar, passing into the pulmonary artery, going to the lungs. From the lungs, we go into the pulmonary veins, which go into the left atrium, past the left AV, into the left ventricle, past the pulmonary semilunar, into the aorta, which goes to the body, including the capillaries, where we then drain into our veins. Whee! Alright, special mention. Some of the most important arteries in the body branch off from the very base of the aorta. Right, if this is your big ol' aortic arch, coming off from the base are the coronary arteries. These are the arteries that bring blood to the heart. Right? So they're branching off the very base of the aorta, and they are feeding blood, oxygen, and nutrients to the heart. And if you have a blockage in one of these, what do they call it? They say you have a coronary blockage, which you probably could have figured it out, but what it's causing is often referred to as a coronary, which is often fancy talk for a heart attack. Heart attacks are caused by blockages in the coronary arteries. Right? Because if I take one of these coronary arteries and I block it off, blood can't get past. Right? There. Okay. Now let's talk about how you control the heartbeat. And it's actually pretty cool. Right? The heart controls its own heartbeat. In the nervous system lecture, you'll learn that a nerve cell sends an impulse, a little electrical impulse, and it's based on charge, with the inside of a nerve cell being a little more negatively charged than the outside. And nerve cells have special transport proteins that control when and how you move ions in and out of a nerve cell to change that charge, right? Well, there are nerve cells in the heart that are what we call leaky, right? And so you have these little positively charged ions that just sort of over time leak in there. It's not well controlled. They just sort of leak into the nerve cell, and it takes a little while. They have sort of a set leakage rate that varies person to person, but eventually you get to a point where the charges inside and outside are equal, and bam, that's an electrical impulse, and that is the impulse that governs your heartbeat. So basically, however long it takes for those ions to leak into that nerve and then trigger the impulse, and then the nerve resets itself, and then they leak, and you trigger it, and then ba, 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 ba. That is the leak. in the nerve cells, these special nerve cells embedded in the muscular wall of your heart. Pretty cool. The heartbeat is in fact not controlled by the central nervous system in any way whatsoever. The central nervous system can influence the heartbeat. It can send signals that can speed up the heartbeat. Like if you see a bear and you need to run from it, your heart's going to need to beat faster. There's a central nervous system reaction that can speed it up. And there's, certain situations where you can relax yourself enough that you can slow it down. The central nervous system can influence your heartbeat, but it cannot directly control it, because the control comes from the heart itself. The heart itself is what sets the heartbeat. And it happens as sort of a wave, right? Up in the top of the heart, we have a region of leaky nerves called the sinoatrial node, or the SA node, right? And they're just sort of right up here in the top of the right atrium. And they are these leaky nerves. And they're called the pacemaker. So, however long it takes them to leak enough to send out an impulse, and then reset and leak and send out an impulse, controls the basic heartbeat of your body. Da-dum, 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 right? It's right up there in the top of the right atrium. And then you have nerve cells running all throughout the muscle of the heart, because neurons control muscle, right? So once that leaks enough and an impulse goes out, the impulse connects up through the atrium. And the atrium, it'll do a little pumping. And then it'll hit the AV node. You've seen AV before. Here it's atrioventricular. Atrioventricular node. It's sitting there between the atrium and the ventricle on the right side of the heart. So that's the AV node, and it's sort of like this little pathway. From the AV node we get to the ventricles. So the SA node communicates with the atriums. Right? So here we go. Signal, we leak and we get a signal, and it causes the atriums to do their little thing, and then we hit here with the AV node, and then we have nerves that come through here and feed the muscle walls. Right? Boom. They're connected. The sinoatrial node generates the signal and sends it to the rest of the heart. From the sinoatrial node to the atria, and from the atrioventricular node to the ventricles. The average heartbeat, probably taken for white men, because so many health facts are averages for white men, but is 60 to 80 beats per minute at rest. And that's just sort of the signal traveling in a very basic animated GIF. Then there's the cardiac cycle. A complete cardiac cycle consists of two things, the systole and the diastole. So, what are those things? Well, the systole is the contraction phase. In other words, during the systole, the ventricles contract. And this is what's pushing blood out to the lungs and body. We are ejecting blood out of the heart to the lungs and body. Systolic pressure in the heart is high because those ventricles are the big muscly guys and they are contracting and pushing. So, 120 millimeters of mercury. In the U.S., millimeters of mercury is a common pressure measurement. But this number is just for you to put it together once I talk about diastole. Diastole is sort of the refilling phase. The heart muscles relax, the ventricles relax, and blood can drain into the atria and ventricles, filling the heart back up. Right? The diastolic pressure is low, generally the average being about 80 millimeters of mercury. So if a doctor wanted to talk about the blood pressure in your heart, he might say it has a systole of 120 over a diastole of 80. Oh, they always give you blood pressure in two numbers. Look at that. It's the systolic and diastolic pressure. What? You learned something. Okay. So, here we go. This is the pumping of blood in the heart. And the nice refill. I just like this image. It's a really nice little image. The atria, just very little muscle, because all they need to do is push a little bit of blood. And the ventricles do the major pumping. Whee! And here is an image with the SA and AV nodes, right? So here's my come back here. So we've got the sinoatrial node getting leaky, and bam, it fires. And it goes out, controlling the atrium. And then here's my atrioventricular node, and it comes out through here, and bam, the ventricles fire. Okay, when you want to measure a heartbeat, you use an EKG, electrocardiogram. They use K because it has a hard sound, and cardio is a hard C. So there's no mistaking what you want when you say EKG. Also, I think it's based on a German tool, and I'm pretty sure cardio is with a K in German. So let's go with that without me actually looking that up to confirm it. That way, if it's a lie, we can see how far it propagates into the system at large. Okay, so basically what they do is they slap some electrodes on your chest, and it detects your heartbeat, right? Specifically, it detects the nodes firing and the muscles contracting. So we can see in the image here what corresponds to the activity there. So this little bump here, this first bump, is when the sinoatrial node fires. And then this big peak here, right, is when our atrioventricular node fires. Right? And then we have the heart muscle contracting, and then it just keeps going from there. And so that's why on the machines in the hospital shows, it's going doot, doot, doot. It's tracking the systole and diastole of the nerve firings and the heartbeat. So that's kind of cool. So now you know what that is. So they're not measuring the muscle actually contracting. They're measuring what's going on with the electrical impulses as things happen. I always thought that was kind of cool. All right, pathologies of the cardiovascular system. First off, hyper, a lot. Tension, pressure. Hypertension is high blood pressure. Then we'll talk about arteriosclerosis, then aneurysm, coronary artery disease, heart attack, angina, and varicose veins. We're finishing it off with a light one because we're just going to pile all sorts of scary stuff on you first. Okay, hypertension, one of the scariest. Doctors are pretty freaked out about high blood pressure for good reason. High blood pressure concerns the pressure of blood in every artery in your body, and there are arteries everywhere in your body. So when pressure is high in your heart, pressure is high in all your arteries. Hypertension is a continuous high blood pressure. Your blood pressure spikes in certain situations. For instance, the dentist I went to takes blood pressure readings for some reason, and I hate the dentist so much. And they took my blood pressure, and they were deeply concerned about my health. And then, like a few days later, I went to my regular doctor, who does not terrify me because they do not destroy my bones, and my blood pressure was normal. So it has to be continuous high blood pressure, which is generally considered greater than 160/95, although I think this might be slightly outdated information. I think they've lowered the upper range. I think they've lowered the ranges here so that more pressures are considered high. So I don't know what the new stuff is. I'll have to check that out and edit that. Anyway, roughly 20% of the entire U.S. population has high blood pressure, and the causes can include heredity, obesity, continuous stress. Your diet can even contribute to your blood pressure, and of course, smoking. Right? How bad is high blood pressure, you ask? Well, high blood pressure in the arteries of the brain can lead to swelling of the arteries and even breaking. High blood pressure in the arteries surrounding your eyeball can lead to increased pressure in the eyeball and damage to the nerves and blindness. High pressure in a blood vessel can cause buildups of fat in the blood vessel to break apart and send little pieces to block parts of your body, including blood vessels in your brain or lungs, causing those to swell up and explode. High blood pressure in your kidney causes kidney damage and kidney failure. High blood pressure in your heart can cause swelling of the coronary arteries. Everything can go wrong. I think it can even influence your ability to get an erection. So, if you're biologically male and that's important, maybe that's what you use as an excuse to do something about your blood pressure. Okay, arteriosclerosis. Fun name. Not so fun pathology. It is a, quote, hardening of the lining of a artery wall. So it's worth noting that the artery has a little thin layer of epithelium lining the inside of it. And we call that lining the endothelium. The endothelium is incredibly smooth. Incredibly smooth. The reason for this is because you have clotting factors in your blood that are responsible for generating blood clots. And clotting factors fuse or bind to any rough surface. They fuse or bind to any rough surface. So in arteriosclerosis, something has caused a part of that endothelium to become not smooth. Maybe it was a little fat deposit, right? A little fat deposit here, and suddenly my clotting factors are landing on there. And then as my clotting factors land on there, they might tangle up with blood vessels. And I might get little blood vessels tangled up in there. And then that might also tangle up more fat deposits, right? And then that'll tangle up more clotting factors. And you'll just get an increasingly large hardening plaque. So, a plaque is a deposit in a blood vessel that is basically an amalgam of various cells, fats, things like calcium, general debris, and clotting factors, right? And those clotting factors, when you get enough of them linked together, they are fibrous. And so it is a hardening because the outside of a thick, developed plaque is fibrous. So, kind of hard. This is often, or this can come in the form of a clot. So, if you have a blood clot that forms, right? This is arteriosclerosis, a hardening due to these weird deposits creating plaques from things like maybe deposited fats or maybe a clotting reaction itself. At any rate, it's worth noting that clots are not something that's in one spot. Like when people think of a clot in a vessel, they think of a thing sort of sticking up in a vessel. That's not how clots work. Clots are long, often traveling almost the entire length of the vessel they're in. My mom has a blood clot in her leg that started, not started, but that goes from basically the part of her femoral artery near the crotch all the way down to her ankle on her right side. Her right leg has a clot going from right near her crotch all the way down to her ankle. So that was a particularly crappy blood clot. She got it after knee surgery because she has a weird genetic defect. So, anyway, they can be dangerous. One of the side effects you can get from a blood clot, if a blood clot has the finger over a hose effect, right? A small clot has a small increase of pressure for the vessel it's in, and the bigger the clot is over time, the bigger the plaque is over time, the greater the effect. And you know, when you put your thumb over a hose, drastically increases the pressure in there. Same thing's going on with that plaque, right? It's increasing pressure. If you have a bad plaque, one of the things that can happen is an aneurysm. The pressure has caused a weakening of the blood vessel wall, and that weakened area of wall is now swelling, right? Often a product of hypertension, because tension against those walls isn't just from plaques. It can also be from continuous high blood pressure. In fact, just to make things even more fun for you, when we go back to arteriosclerosis, if you think about those arteries, right, they have to expand to handle pressure. Well, if you have continuous high blood pressure, they have to expand even more, and at a certain point, they'll reach an expansion limit, and you can get tearing of the endothelial lining due to just your high blood pressure. Right? That's an endothelial shear. And guess what, folks? because your artery had to expand beyond the limits of the endothelium and you got a little tear, that tear is rough. So high blood pressure can cause plaques. Whee! So, not only can your artery be weakened from just having to take high blood pressure all the time, the plaque that your high blood pressure might have caused can further increase pressure and weaken the wall. And if the wall gets weakened enough and there's enough swelling, you can rupture your aneurysm. And that is bad. That causes internal bleeding, right? So, there are certain places where it's not great to have an aneurysm anywhere, but here's my person. Hey, I'm happy. I eat a lot of steak. The fattiest parts only. Well, probably not that. Anyway, right? In this person's face is his skull. And inside this person's skull is an opening for this person's brain. And guess what? The skull is made of bone. And the bone can't expand. And if you have an aneurysm that ruptures in the brain and you start filling that cavity up with blood, well, now you've got extra stuff you're putting in there, and the brain can't, cause much expansion. It just hits that skull and gets pushed up against it, and the tissue dies. So, an aneurysm, a ruptured aneurysm, is one of the major causes of stroke, bleeding in the brain. We'll talk about strokes when we talk about the nervous system, but bleeding in the brain is a stroke, and that can be caused by a ruptured aneurysm. So, the reason it causes brain death is because, things are pretty tight quarters in that skull. And if you try and take the brain and push blood in there, you are increasing the skull pressure a lot, the cavity, the brain cavity's pressure a lot. And pressure on brain cells kills brain cells. And so that's why strokes cause brain death. Okay, coronary artery disease. This is highly correlated with cholesterol, specifically low-density lipoprotein cholesterol. Cholesterol that doesn't dissolve in blood near as well as high density, right? It doesn't dissolve as well, and so LDL is prone to making deposits on the endothelium, and that causes plaques. So coronary artery disease is associated most with high LDL levels, and of course we're specifically referencing to plaques forming in the coronary arteries. Right? This is bad because when you cut off blood flow, if you completely block blood flow in a coronary artery, all the muscle it feeds dies. Right? Heart muscles need oxygen. Heart muscle absolutely needs oxygen. Skeletal muscle can actually operate without oxygen. If you remember forever ago to the fermentation lecture, or the part of the lecture where we talked about fermentation, skeletal muscle can actually generate the ATPs in the absence of oxygen. Cardiac muscle can't do that. So if you cut off oxygen flow to the heart, because of a plaque in a coronary artery, then the heart muscle starts to die. This is not something your brain and body recognize as a good thing, so that generally causes your heart to freak out. And we'll talk about that in a moment. Okay, so there are various treatments for plaques in general. One of the most common ones, but is becoming less used, is a little net thing. But first, with blood clots themselves, if you catch it within 3 to 4 hours, they can give you a clot-busting drug, like streptokinase. If the first part of this, strep, looks a lot like strep throat, well, guess what? The Streptococcus bacteria is a pathogen, a disease-causing bacteria. And one of the nasty ways it causes disease is by breaking down clots and digesting blood. Breaks clots and digests red blood cells. Like, it's pretty nasty. But we did in fact find the enzyme, ASE tells you there's an enzyme, that causes breaking down of clots, and we were able to manufacture it. So we have a drug containing streptokinase that if it's been within like 3 hours of getting a clot, they can administer the drug and actually just break down the clot. So if it's a blood clot that's causing your problem and not just a fatty plaque, a clot-busting drug can be administered. Angioplasty is one of the more common ones. It's a non-bypass system whereby you can try and reduce the size of the plaque. Basically, they just thread a little wire carrying the little wire net into the blood vessel that has the plaque, and then they inflate a little balloon that pushes the net up against the walls of the blood vessel, and the net flattens out the plaque a little. Right? Recent research has actually shown that this carries its own risk, and that younger people for whom lifestyle changes would be an excellent way to treat the stuff. That's actually much more recommended than angioplasty. It used to be thought that angioplasties were like a really harmless, easy treatment. But anyway, a relatively easy treatment for plaques. But as it turns out, more research is showing that they're not exactly ideal for certain groups of people, like us youngins. Yes, I belong to the young still. Anyway, flattens out plaques by having a little balloon expand a little mesh net up against the plaque. And then there's bypass surgery. Right, so here's my blood vessel. Right, and here's my plaque, and it's built up, and it's causing danger. Right, well, what I can do is I can go into your leg and grab a chunk of vein and cut a little section of vein out, and take that section of vein and just cut a little hole in the artery on either end there, and what do you know? I have a bypass. Fluid follows the path of least resistance, so it will just go through my bypass and safely bypass the plaque or clot, and that basically just removes this from causing that pressure. And so it reduces the danger of weakening and aneurysm and ruptured aneurysms and death and everyone dies, we're all going to die. Anyway, they transplant a vein, a large vein, usually from the leg, onto a artery with a thick blockage. and they create a blood bypass. So, here's your blockages, and they just graft veins on there. Right? And that way, boom, you are avoiding the blockages. The number of veins they have to graft on during your surgery determines whether or not they call it a bypass surgery, a double bypass surgery, or, as in the case of this particular picture, a triple bypass surgery. Aha, now you know why they call them double bypasses or triple bypasses. Learning! Alright, the heart attack. So generally, you have a plaque in a coronary artery, and it blocks blood flow, and, you know, the heart muscle can't ferment, and it starts to die. Regions of the heart muscle start to die. This is bad. The portions of your body for detecting this freak out, right? So, angina, pain, or not pain. Angina is, pain. Pain in your arm. Pain is, angina is heart pain. Pain in your arms and back. Numbness in your arms and back. Trouble breathing. These are all symptoms of a heart attack. And then the key thing to what's happening in a heart attack is when you lose rhythm. This here is a normal rhythm. So you can see the wave, the false coloring in this image is the white being, the black area is the nerve impulse, right? And so you start up here, atrium, it's hard telling the whole thing. But anyway, you get these nerve impulses as waves. Waves of nerve impulses, atria, ventricles. So, right? Pretty simple. Over here, we've lost rhythm. Right? This is an arrhythmia. Maybe I spelled rhythm right and freaked out over nothing. I'm getting old, man. I can't remember how to spell stuff anymore. An arrhythmia. We've lost rhythm. You can see there's no rhyme or reason here. Your heart will be like, right? Sometimes you have atrial fibrillation, where you could think of it almost like the muscles in the atria are like vibrating, right? They're sort of like so that's atrial fibrillation. So you are losing rhythm in your heart. It's not pumping blood correctly. You're having atrial fibrillation. And if this goes on too long enough, if the heart dies, that the heart shuts down and stops beating, right? They have a chance of reviving you, and your heart might repair itself, but after every heart attack, generally you have a certain percentage of permanent damage, right? Every heart attack causes permanent death of heart tissue. Permanently kills heart tissue. This means it is harder and harder to survive successive heart attacks, right? So, If they can revive you after that, depending on how long your heart had stopped and how long you were without oxygen and how much area got blocked off, you'll have a certain percentage of your heart permanently killed, and you'll have a reduced capacity for pumping blood and basically a reduced capacity for activity. By the way, in movies, you might have seen a tool called a defibrillator. Right? Everyone uses them the same way. When someone's having a heart attack, of course in a movie, you know they're having a heart attack because their little heart meter goes dee, and they go, grab the paddles! And they go, rub them together, clear! Zig-zag! And zap ya. And usually it takes like 3, and then the doctor has to be like, fight! Fight, damn you! Fight! And then they're like, again! And they're like, doctor! It's been too long! And they're like, again! Turn it up! And the funny thing about all that is that once the heart monitor went dee, the defibrillator became useless. 100% useless. Right? Because a defibrillator uses an electrical jolt to reset your sinoatrial node back to its normal pace. Right? A D on the monitor means there is no electrical impulse from the sinoatrial node, so there is literally nothing to reset. The only thing you can do in that situation is like compressions, or even like literally massaging the heart, trying to keep oxygen and blood pumping enough to see if you can get it going again. Defibrillators are used before the heart stops. You can only use a defibrillator when the heart is going, right? Even if it's a very weak heartbeat, that's time to use the defibrillator, because a sudden electrical jolt often causes a sinoatrial node to reset back to its normal pace. I don't know. I thought that was kind of cool. And lastly, let's get a little less crazy with the varicose veins. Varicose veins are most often seen in the elderly, right? They're when you have very large, thick veins, swollen veins. Veins appear blue. The blood is still red. It's just the fact that it's not carrying near as much oxygen, it just appears blue in a vein. Your blood is always red. Anyway, you've got these thick, blue, swollen veins. And what's happened here is that in varicose veins, you have damaged valves. Those valves, when they snap shut, prevent blood from backflowing. Well, if you've damaged the valves, blood is free to backflow. And so you'll have this muscle pumping blood. You have a muscle down here pushing to pump blood up, but the blood can backflow down, and basically around that damaged vein we get swelling. Right? So varicose veins are literally swollen areas of veins because our little venous valves have been damaged and they can no longer prevent backflow. And so the veins have swollen. If the valves around your rectum, right, around your anus itself become damaged, right, the venous valves around the anus, you can get swellings of the blood vessels right around your anus, and those are hemorrhoids. So you take anti-inflammatory drugs or creams to try and reduce the inflammation around those veins, to try and reduce the swelling. Generally, you can only cure a varicose vein by literally removing the swollen vein. Right? Rest can often cause things like hemorrhoids to reduce over time. So, if you're young and your body is still doing its thing pretty well, sometimes rest and relaxation can help out. Hi, were you asleep? You were moving around a bunch. So sometimes rest and relaxation is enough to help the body repair those damaged valves. And last but not least, you have surgical interventions where they literally remove a section, right? So here's hemorrhoids, generally from pressure in the veins, like high blood pressure can cause pressure in the veins, and your veins really can't handle that much pressure. Or, for instance, if you're a strainer and you're straining those muscles, you can tax the veins, and it causes damage to the valves, and they swell. And so it can happen outside your anus, and you get an external hemorrhoid. It can happen inside the valve, right? Or valve, the sphincter. It can happen beyond, like, the anal sphincter, and you get an internal hemorrhoid, which is very painful. Or you can just win the lottery of pain and have a hemorrhoid so big that the area of vein swollen goes from inside the sphincter all the way to outside the sphincter, in which case it's extremely painful. So, anti-inflammatory drugs, creams, and drugs to rub on the affected areas. At rest, to try and see if your body's repair mechanisms can handle it. Boop, boop, boop. And if all else fails, surgery.